Autonomous ships are no longer science fiction. They are navigating real waterways, but their ability to survive in complex maritime environments hinges on one critical capability: situational awareness. And situational awareness doesn't come from a single sensor. It comes from fusing them. But fusing maritime data is notoriously difficult. The automatic identification system gives you identity and motion, but updates slowly, drops signal, and can't see non-cooperative vessels. Marine radar sees everything, but its accuracy degrades with distance, and it gets swamped by sea clutter. Cameras provide rich semantic detail, but they lack direct dynamic state information, and monocular distance estimation is fundamentally unreliable. So how do you stitch these heterogeneous data streams into a single, continuous, and trustworthy perception layer? The answer lies in a new framework called NavEYE, a vision-centered multi-sensor fusion system designed specifically for intelligent surface vehicles. Instead of treating sensor fusion as a simple averaging problem, NavEYE tackles the three core failure points of maritime perception: cross-sensor data association, adaptive fusion under distance-dependent error, and seamless trajectory stitching during sensor dropout. Let's break down exactly how it works, the mathematics behind it, and how it's deployed in practice. The first step in any multi-sensor system is matching observations to the same physical object. In maritime navigation, you're constantly trying to link a slow-updating AIS track with a fast-updating radar return. Traditional statistical methods like joint probabilistic data association or interacting multiple models struggle here. They rely heavily on prior assumptions about noise distributions and motion models, and their performance collapses when traffic density increases or ships maneuver unpredictably. NavEYE solves this with a multi-constrained gated association method. Instead of relying on a single feature, MCGA builds an association cost matrix using 4 dimensions: latitude, longitude, speed over ground, and course over ground. Because these variables have different physical units and uncertainty scales, you can't just compute raw Euclidean distance. The method normalizes the residuals using a Mahalanobis distance metric, which effectively weights each dimension by its inverse covariance. This accounts for the fact that, for example, course angle has a periodic boundary and position error scales differently than speed error. A gating threshold filters out physically impossible pairings, and the Hungarian algorithm then solves for the globally optimal one-to-one assignment. The result is a robust association layer that maintains high precision even in narrow channels and port anchorages where ship crossings and occlusions are frequent. Once objects are associated, you need to fuse them. But you can't apply a fixed weight. AIS position error is dominated by GNSS baseline noise, which remains relatively constant regardless of range. Marine radar error, however, is fundamentally distance-dependent. As a target moves farther away, the radar beam width and cross-range resolution limitations cause position uncertainty to grow quadratically. NavEYE captures this with a distance-aware, adaptively weighted fusion model. It establishes explicit error variance functions for both sensors. When a target is close, the radar's superior spatial resolution dominates the fusion weight. As distance increases, the radar error term balloons, and the fusion naturally shifts reliance toward the more stable AIS track. This dynamic weighting prevents the system from overtrusting degraded radar returns at long range, while still leveraging radar's precision at close quarters. But real maritime environments are messy. Detection range limits, sea clutter, and communication dropouts mean your system will constantly switch between dual-source AIS radar observation and single-source fallback. A naive approach would simply replace the fused track with whatever sensor is currently available. That causes immediate trajectory discontinuities, sudden jumps in position, speed, and course that can destabilize collision avoidance logic. NavEYE addresses this with a timeliness decay-based stitching fusion mechanism. When a sensor drops out, the system doesn't just switch. It treats the last known fused track as a reliable prior estimate. Using linear extrapolation based on the previous 2 fused states, it predicts the object's current position and velocity. Then, instead of hard switching, it blends this prediction with the new single-sensor observation using an exponential time decay function. The weight of the historical prediction decays smoothly as the time delay increases, while the weight of the live observation rises. This creates a mathematically smooth transition that eliminates position jumps and maintains trajectory continuity, even during prolonged single-source gaps. Now let's add the camera. Vision provides the semantic context that radar and AIS lack. You can actually see the ship's hull, superstructure, and navigation lights. But mapping a 2D image coordinate to a 3D geospatial track requires solving a cross-modal alignment problem. You can't just project pixels onto a map and hope for the best. Monocular depth estimation introduces too much uncertainty, and bearing-only constraints fail when multiple ships share similar relative angles. NavEYE's Vision AIS radar fusion method solves this by constraining association with 2 normalized features: relative bearing and relative distance. For geospatial tracks, bearing is computed using spherical geometry between the own ship's GNSS coordinates and the fused track, then converted to a relative bearing using the gyrocompass course. For the camera, bearing is derived from the pixel offset of the detection box relative to the image centerline, mapped through the camera's intrinsic focal length. Distance uses the Haversine formula for geospatial tracks, normalized against the radar's maximum detection range. For the camera, it exploits the monotonic relationship between the bottom edge of the bounding box and actual range. Lower in the frame means closer. These normalized features are combined into a joint cost matrix, again optimized with the Hungarian algorithm. By requiring both bearing and distance to align, the method drastically reduces association ambiguity in dense traffic, where single constraint approaches routinely swap identities between neighboring vessels. All of this theory needed real-world validation, so the researchers constructed the MAP fusion dataset. It's not a simulation. It's 135 minutes of time-synchronized, shipborne data collected across open waters, narrow channels, and high-density ports. The dataset includes over 8,000 video frames, thousands of AIS tracks, and thousands of radar returns. They fine-tuned a lightweight YOLO 11N architecture on this domain-specific data, creating ship YOLO 11N. This wasn't just a marginal improvement. Fine-tuning on maritime imagery, combined with high-resolution input, pushed detection accuracy well above baseline models, particularly for small, distant vessels that dominate open-water scenarios. The experimental results confirm that every component of the framework does heavy lifting. The multi-constrained association method outperforms traditional JPDA, MHT, and gray relational association across all traffic densities. The adaptive fusion model reduces trajectory deviation metrics by nearly 30% compared to fixed-weight averaging and standard Kalman filtering. The stitching mechanism cuts position jump distances by over 80% during sensor dropout. And the vision fusion method achieves over 80% cross-modal association accuracy, compared to roughly 30% for coordinate projection or bearing-only methods. But an algorithm on a server doesn't navigate a ship. NavEYE is deployed as a complete engineering system. The hardware stack integrates marine radar, AIS, GNSS, gyrocompass, and an RGB camera into a local network. A dedicated data hub handles protocol decoding and preprocessing for the geospatial sensors, pushing structured data via MQTT. The camera stream is sampled, encoded, and transmitted over gRPC to an industrial computer running a multiprocessing Python pipeline. This architecture separates sensor I/O from heavy computation, ensuring real-time performance without bottlenecking the data pipeline. The software processes everything end-to-end, outputting fused tracks, collision risk coefficients based on DCPA and TCPA calculations, and intuitive visualization panels that overlay MMSI, position, speed, and heading directly onto video feeds and electronic charts. This is where academic research meets maritime engineering. Autonomous surface vehicles require perception systems that don't just work in ideal conditions, but degrade gracefully when sensors fail, traffic density spikes, or environmental noise increases. NavEYE's framework provides a mathematically rigorous, computationally efficient solution to the core problems of maritime multi-sensor fusion. It replaces brittle fixed-weight assumptions with distance-aware adaptive weighting, eliminates trajectory discontinuities with exponential decay stitching, and bridges the vision geospatial gap with dual-constraint cross-modal association. The research team acknowledges that real-world deployment still faces challenges. The current system and dataset are optimized for normal visibility and illumination. Low visibility, heavy rain, fog, and strong backlighting will require additional robustness. The distance proxy using bounding box bottom edges is also sensitive to camera pitch variations and wave-induced occlusion. Future iterations will likely incorporate EMU-based attitude compensation, more advanced visual distance modeling, and expanded environmental coverage. But the foundation is solid. As autonomous maritime traffic moves from controlled trials to commercial operations, the demand for reliable, multi-sensor situational awareness will only intensify. NavEYE demonstrates that by respecting the physical limitations of each sensor, modeling their error characteristics explicitly, and designing fusion logic that anticipates real-world switching behavior, we can build perception systems that are not just accurate, but resilient. The future of autonomous navigation isn't about replacing human senses with better sensors. It's about fusing imperfect data into a coherent, continuous, and trustworthy understanding of the world. And that's exactly what this framework delivers.